Okay. Well, thank you very much. Thanks for the introduction, for the lengthy introduction. And thank you all for being here. Uh, well, I'm gonna teach a subject which maybe not so much into your CV so far, but when I was asked to give lectures here, I thought that that is something that little by little is winning more momentum in current ideas of how to look for beyond the standard model physics or gravitational waves. And the ideal situation is that the new students, you, start to be more, you know, used to those techniques, and then eventually there will be some synergies with the other topics of quantum sensing and quantum techniques in general. All right, so the way this works is questions at the end, right, Michele? During? All right. All right. So by training, I am also a theorist, like hardcore in gravity and particle physics. But as I said, I think that these new ideas are very important for us these days. So the main structure is, well, first I'm gonna spend a couple of minutes more on why. Then we are gonna discuss something about states of signals. Okay. Here you will understand, I hope, what about this topic. In particular, single particles, coherent states, and stochastic, well, fields. Okay. Each of those correspond to different ways in which new physics can come to us. And normally you don't talk about those, but it's more important. Then I will talk a little bit about the coherence. In the end, the coherence is 15s. And those are mechanisms by which environment system, and again, if you are looking for new physics, you can always understand the new physics as environment, and your detector, in this case, it's going to be a quantum detector. So looking about this, the coherence or phase shifts, you may be able to learn more about what's going on around the detector. I hope this will be today, tomorrow, more or less 1 or 2, 3 days. And then I will talk more about quantum sensing by itself. And here there is it's a full body of many people working on it. So myself comprehend. The idea is we are going to discuss something about the back action. So what are the limits that quantum mechanics set on any kind of detector? And how do we, these days, try to be clever and manipulate our states to beat the standard quantum limits, which in the end is a must if we want to detect the most feeble signals. All right? All right. So now for the why, because it's enjoy these lectures, you'll see that many of the things we are gonna discuss are things that are fundamental questions that somehow when you do quantum field theory, they are always left aside about them. But when you start thinking about what when there is a decay, when there is thermal production, when there is whatever, what kind of states, you relate as a process, then some of the questions have been already asked, some some ways to answer. interesting just conceptually as a theorist. So it's important if you want to detect new particles to understand which kind of you are looking for. Now, the second point of why is because in the end, we have particles which are, well, new signals, and typically signals are to detect. And this is happening in other frontier of physics, right? There is a frontier of quantum sensing or sensing where people are also in the try to beat, the most precise ways to find any kind of force or any kind of pressure on a system. And for sure, this is something we want to also leverage to and what else is there in the universe, right? Coming from new particles and that we can understand. All right. So there is a synergy still to be built between quantum sensing and high energy physics, gravity. And the good news for you is that there are very few people, maybe one or two people in the world, who can make this bridge. That means that if you are in this field now, it's a field that is being built as we speak. So there is the chance to have an impact, right? Because not, I can tell you, well, I had to study a lot for the lectures, for instance, and I'm not the only one. So there are many things that are still being developed. So that's why it's also nice. Okay. So first, for why, let me also within the why give you three examples of maybe relevant for the. If you think about your career as researcher, what can happen in your future that may have an impact for the rest of humanity. Okay. So one of them has to do with neutrino physics, right? So neutrinos are particles that are, in particular, their mass is not understood. Well, not understood, it's not known. Their flavor structure is quite weird. People try to explain it. But also, for instance, it's not clear which kind of particles there are, whether they are Majorana, Dirac. And with this, what I mean is that there are still mysteries to be understood about neutrinos. As to find those mysteries, you can try to look at the universe, places where there are neutrinos around, and understand them. In the early universe, for instance, there were neutrinos being emitted. In stars, there are neutrinos being emitted. In reactors, there are neutrinos being emitted. And the idea is that today you can try to look for these on Earth. Okay, so there are fluxes of neutrinos from, well, the universe, early universe, stars, reactors. And here you find the first difficulty, that the neutrinos interact through Fermi interactions, which are very much weak, right? So you can a neutrino flux now, for instance, in the Big Bang paradigm, there is a neutrino flux generated in the early universe way earlier than CMB. Well, CMB, so this is called the CNB, cosmic neutrino background. No one has seen it yet. Whoever sees it, well, it's gonna be famous for the rest of the history. Of course, we don't do this for this, but anyways, it's a goal. And the problem with these neutrinos is not that they are not going through us. There is 10 to the 12 neutrinos per centimeter square per second generated at the Big Bang. Okay, so the flux is not that bad. The problem is that they are non-relativistic and interact through weak interaction, so very hard to detect. Okay, so these flags, how do you want to detect it? Well, of course, it's going to be the most tiny possible signal. So you want to understand how to detect possible weak signals. And same happens with the mass. The mass of the neutrino is a very small effect because neutrinos typically today are produced relativistically. So it's very hard to. So here, certainly, any kind of quantum sensing may be impactful. But neutrinos are not so, they are not discussed always when people discuss BSM, because in the end they are in between SM and BSM, right? Because we know they exist, so they are standard model, but there are some features of neutrinos which we don't understand. If we start looking about new particles, the first one that comes to mind is dark matter. No? Dark matter, well, we are gonna assume dark matter is particle-like. And for dark matter, again, how do we want to detect dark matter, or even understand what is dark matter? We need to know something about how much dark matter there is around us in order to answer this question. For this, if we draw a line and we ask for the more fundamental question about what is dark matter, we know it's non-relativistic, so it has a mass. Otherwise you cannot cluster in galaxies. And this mass can go all the way from 10 to the minus 21, 22 eV to whatever even the cutoff of the theory. So let's say 100 TeV. I mean, you cannot go to Planck because at some point it crashes, but this huge range of masses where dark matter can be living as a particle. All right. Now, how do we detect these possibilities? Right. How do we go and say, well, we're gonna really build an experiment to find this guy? We need to know more about what this is. In the same way that for neutrinos we know everything, for here there is a lot of freedom. We know that dark matter in our solar system environment weighs more or less, 1 GeV, okay, so 1 neutron, more or less, per centimeter cube, by 1.4, the same. So there is not that much amount of dark matter around us. And we also know that the typical velocity of dark matter is 10 to the minus 3 speed of light. By the way, speed of light, I'm going to use natural units, except when I use natural units, but in principle, I will use them. Okay, so with this, we can already start playing a game, and the game is going to be, okay, which kind of models of dark matter can I detect with the big detectors, right? And this is equivalent to saying I have a dark matter particle. Does anyone know if this what is the wave packet of this dark matter? How do you determine it? It's going to be a particle or it's going to be a super spread particle? So it is a localized, or what characterizes the dark matter as a particle? Okay, we're going to discuss this in a second. But just imagine that this is a localized particle, then it hits a detector, and then it can recoil and make the nucleus recoil, right? Now, if you do some algebra, you can, with the just kinematics, you can find that the maximum recoil energy with this possible velocity and this possible energy density is given by 10 kilo electron volts, mass of dark matter, 20 GeV, and here the mass of the atom. Okay, well, of the nucleus. All right, so this is the maximum energy that you can inject, because basically you absorb, there's no absorption, there is a scattering, but basically this stops, right? So you really absorb all the kinetic energy. The maximum you can get is proportional to the mass. Of course, the more energy you bring in, the more energy you can deposit. And inversely, this is, by the way, in the limit of the dark matter much smaller than the nucleus, okay, which is what this is basically, what this formula already has in the numbers. So in this case, you cannot deposit more than 10 kilo electron volts if the mass of the dark matter is around GeV. That means that for masses below GeV, you need a detector able to see energy depositions of kilo electron volts to detect it, okay? Otherwise, you can have a flux of billions of millions of particles, but you're not gonna see anything, right? Because you need at least, this has to be bigger than the energy of threshold. What is the threshold of these huge detectors that you see today around, around the Earth? Does anyone know? Maybe someone does dark matter phenomenology. 1 kilo electron volt, okay, more or less. It makes sense. So you have a huge tank of, these particles flying around. You try to cool them down, but it's one, 1 keV is kind of the average thing you can do with, even with 1 ton, 10 tons, 100 tons. It doesn't matter. You can make it bigger and bigger, and you will never be able to see dark matter below GeV. So what do we do with all this? What do we do with all these models, right? So clearly, a way to go is to build detectors which have thresholds which are smaller than keV. And then again, you can see this amount of energy for a very precise sensor is not that little. So for instance, electron volts ionize, kilo electron volt is when you hit the nucleus. So in principle, I mean, there are ways to beat this, but then the problem is that then you cannot build it very big. So there is always some threshold, some balance. But for sure, here is where technologies that allow you to read out a small amount of energies are going to be competing, and is where, again, there is a lot of things to discuss. Because people, since the 80s, for dark matter, they focus in building detectors in this regime, right? Because the WIMP paradigm, everything works very well if dark matter has a mass of, 20, 100 GeV. But in principle, all this landscape is waiting for, for new detectors. Of course, there are ideas, but let's say that the road is still not so much walked as the walk of the WIMP. And finally, by the way, you can do the same with fluxes from colliders. There is a collider, and then out of the collision, there are some new particles being emitted. What happens if these new particles bring energy which is smaller than the typical thresholds around you? So having a detector that has less threshold sensitivity is always good, no? If you want to detect, for instance, a huge flux, which is low energy. So also for this kind of for collider phenomenology of detector, also having better sensors is always good. And finally, the third aspect that I'm going to discuss of why is gravitational waves. Okay, gravitational waves typically described as waves, not as individual particles. We are going to discuss this a little bit today. And that means that normally you characterize them by an amplitude and a frequency, okay? And the problem with gravitational waves is that this is typically very, very small, okay? So you want to see, for instance, the formations of space-time, which have to do with the gravitational waves of the order of, I don't know, 1 atomic size. Of course, this requires techniques that eventually can be big. Okay, quantum is not always small. Like for instance, what people do in LIGO, Virgo Cagra, they use quantum techniques for big macroscopic objects. But you can imagine that these days, also because of this revolution in quantum sensing, there is also a lot of interest on applying it directly to detect gravitational waves. Okay, so if anyone is not convinced that you need this for your future, let me know. But I think is any questions? Well, so then let's move on to the first part of the lectures. State of states of signals. So normally, again, when you think about new particles, you think of them as a wave packet, I hope. All right, each particle is characterized by some momentum distribution, and with this distribution, you have the particle itself, the, the wave function, right? That is, it's never a single momentum. Remember, a single momentum state, if you find how does it look like in space, is fully delocalized. So you are thinking about individual particles. What the wave packet does for you is generating something that is localized in space, right? And then this spreads and evolves with time. Quantum mechanics, everyone has done, I hope. Normally, again, when you want to do real things, you have to put the wave packet in. The wave packets, even in quantum field theory, typically they are only put at the last stage of the calculations, which is also good. People have shown in the 60s and 70s that that's fine. If you read the book by Weinberg, he says it very clearly that all these burdens eventually are easy to incorporate, but at some point you have to put them in, okay? So you can, in other words, you can do quantum field theory with wave packets, not with momentum states. The good thing is that everything you compute is physical. Some of the things you compute in quantum field theory that are divergent or these kind of things are because you are not using the real physical states. You are using ideal states, okay? And using wave packets allows you to go and do physical things, but computationally is harder because you have to keep phi's all over the place. And, as I said, people already understood this in the 60s or 70s, and eventually this is not so relevant. Well, all these things come back, no? I don't know. People now are using amplitudes methods, not for momentum states, but for energy states. I don't know, you have heard. People may be more theoretically inclined. Energy correlators are important these days. So in the end, you have to understand something physical about what you are doing, in particular when you find divergences. Well, this wave packet, okay? How it is generated, what is the typical size? So eventually, in in space, this is gonna be something like, imagine that this is a wave packet localized around 0, okay? So this is basically your particle, and it has some spread, some dispersion, right? That it has to do with the state of generated by it, okay? When you think about generation of real particles, there is one field where this is very important, is in neutrino physics, because when neutrinos interact with the atoms these days, they want to understand if the scattering is coherent, not coherent. So you want to really understand how to derive the wave packet of a reactor. My advice is that you read some neutrino. You can look for neutrino wave packets, and they will give you in all detail. For me, the only thing that matters is that you have a decay from, let's say, particle 1, particle 2. Well, you generate particle 3, all right? And this is going to have some rate. Okay, so it takes some time to be emitted. And with this, remember that there is a kind of uncertainty relations for energy versus time of processes. It's not about operators. If you have never seen this, it's a bit basically what neither energy or time. Well, time is not an operator, so it's not the same kind of thing that happens for p and x. But you can see that when you localize something a lot in space or in time, you delocalize it a lot in energy and vice versa. You can read about it in Sakurai book. It's very well explained in quantum mechanics. But this already gives you that if it takes some time gamma, one gamma to generate a particle, then the typical dispersion that you generate is gamma. Okay, so that's the order one thing. So when you generate a particle at rest, this is what you do. You are the guy here in the appropriate units have to be like this. If when you generate it, these guys are in a thermal, not in an exact state, but they have also some dispersion, okay, delta P of the original guys, then also, because delta P, delta X also satisfy more or less the same relation, the wave packet is also going to be delocalized by delta P. So those are the two main things that tell you, given a process, what is the size that dominates in the wave packet that you generate. All right. So now, if you want to understand what is the typical wave packet size of dark matter, well, you can see how do you generate it in the early universe, which was the typical rates and the typical momentum. Okay, and with this, you can give an estimate of the wave packet at creation. Okay, so all these particles, in a sense, are created with this kind of features. But now, and here is the puzzle, what happens with a wave packet which is localized as is time evolving? A wave packet of massive particles. Does anyone remember? You know. No, you. Yes. It spreads. So the dispersion, because the wave packet is made of different momenta, each momenta has a different speed of propagation. I don't know. When you compute the velocity at which different momenta propagate, suppose group, you can see that this is given by this guy. So you take the, sorry, this is the velocity. You take the dispersion relation and you take the derivative with respect to the momentum. And if the dispersion relation is that of a massive particle, then this velocity is momentum dependent, right? You can do it like this, or you can just take the wave packet and make it evolve freely, okay? With the Hamiltonian being, remember the Hamiltonian is p squared over 2m. Okay, then the wave packet, each momentum evolves differently. That means that with time, the dispersion grows, and I'll put it back now. T squared. All right, so yeah, this is not the best writing, but okay. Original dispersion, 1 plus t squared divided by n velocity dispersion square. All right, so as time grows, individual particles, no matter how you produce them, they tend to be more and more diluted. And now you can ask, how come then we describe dark matter particles as individual particles? As not as a collection of these guys. And this will be more clear tomorrow when we think about the coherence. So when particles see an environment, the environment also localizes them. All right? And this is beautiful. And again, it took some time to understand and then, yeah, hopefully tomorrow we will understand it better. But anyway, this is the simplest possible example. Particles generated. And now if I have a detector, with this, I can, for instance, I can see, well, if my detector is bigger or smaller than sigma, am I gonna be the particle as a single particle, or if my detector is this size and the particle is this size, when it goes through it, it's kind of coherent, no? Because when it goes to the first one or the second, eventually the particle is seen as a single disturbance in the whole nucleus. For instance, this can be a neutrino scattering with two nucleons in a nucleus. If it is more localized, then it will scatter with them independently. And then this, for instance, is important when you want to understand how your signal is seen by a device or an atom which has some size by itself. So coherent versus incoherent. All right. Now, more fun is what happens with the gravitational waves. So I'm going to jump to gravitational waves. Not only gravitational waves, but any kind of state which is generated by a classical source and which is bosonic. So now imagine that you want to give a quantum description of gravitational waves. Do you have an idea how to start? The state of a gravitational wave or a classical field in general. You say a plane wave? Okay. Who said coherent state? Yeah, it's not it's a coherent state. Or anything. So you cannot describe it. If you want to describe it like this, it's gonna be quite hard. Okay. So now, if you want to describe states generated by classical sources, those can be also, for instance, a current of electrons. Those are coherent states. Okay. Again, this is something that was understood a bit earlier. There quantum optics, but still, it's not so maybe familiar to everyone. So let me give you a reference. Well, there is this book. It's Kinson and Suber of quantum field theory, chapter 4.1. I'm following it. So in this case, so you take a quantum field. Okay, I'm gonna take in this case a photon, and now if it is interacting with a current in the Hamiltonian of interaction or in the Lagrangian, eventually when I want to solve the question for this field, okay, I'm gonna find that those are gonna be the ones that you get for electromagnetism source by the current. So no? Is there anyone in the room who hasn't seen second quantization? Okay, and with photons, everyone. So you cannot with the with scalar field, but because I'm following it, they do it with the harder spin one field. Yeah, so this term you can forget about it in the proper gauge. Okay, you can take this gauge, and eventually what you want to solve are the equations of what is going to be the state of this guy. Well, you have to solve the free evolution, but now with the source, right? You can take A, the quantum field as a free state, as a free field, plus then a field that basically it takes into account the current, right? And you take the green function of this operator and you evaluate it on nu. Okay, so this is the solution of the quantum field theory equations in the presence of a source. So normally or if there are more interactions, this is a bit tougher. You have to do quantum field, Feynman diagrams and so on and so forth. When there is only a classical source and a free theory, things are kind of easy, okay? All right, so now you have to to be a bit more careful and impose boundary conditions. Right? Remember that when you have an operator and you compute the green function, you have to put some boundary conditions. And what is also in the free field, when you do S matrix, the asymptotic states also know something about whether you are going. It's not the same to have free states at plus infinity than free state at minus infinity. Okay, so you have to be a bit careful when you define both the free field and the green functions here. Okay. In the end, it's very easy to at least put words into the two possible scenarios. One of them is that here I want to define the free asymptotic field at plus infinity in time. All right, and then I put here the free out operator. And in this case, I have a state that when I go to infinity is described by this guy. So here I have to put the advanced propagator. Okay. Which is a propagator that at plus infinity vanishes. If I want to do the opposite, right, in terms of the in free states, then here I have to put the retarded propagator. Okay, which is the one that it is 0 before the source, right? And from here, you can connect in and out. So you see, you want to know what is the out given an in, well, here is what you have to solve. Okay, so the out state in terms of free fields is A in plus retarded minus advanced. But this guy here, you have done some, study of grid function. This has a name. It's typically has a minus name. When there is a plus, it's plus. Sometimes it's when you separate it into some analytical pieces is the Feynman propagator. Okay, you have never seen this, doesn't matter. It's the advanced minus the retarded minus the advanced. Okay. Why am I doing all this? Is because when you have states, from the, define from the or from the in free states. If you want to evolve them with time, then you define a matrix that eventually generate the out state. So you started with the vacuum. The S matrix of the vacuum generates the state that you have at the end. Right? This is an operator that, if you want, is defined by this. When you applied it to operators, remember that operators evolve. Well, by the way, S is a unitary operator. Well, it's based on unitary evolution. So that means that S and S dagger are related. It is out, in. So, in other words, a way to find this operator itself, if I know the out field in terms of the in field, well, I can try to, solve this equation and try to find what is this S operator, okay? There are other ways to find S. For instance, you can just try to solve, in other books which are not in quantum field theory, but in quantum optics, S is found directly integrating some equations. Here, that's a way in which, I can go from this expression to an expression for S. And to do that, I use our most beloved formula, which I didn't write. Where is it? Here it is. You remember this? Okay, with operators. So here, if I write S as e to the power a, this is b plus a b plus 1/2 a b. And with this, I can identify the different pieces, So the different, I put this back here, and I can identify the pieces in this with the pieces in this expression. And after some algebra that you can find in the book. I like this book because some of the books on quantum field theory, which are older, they also spend more time doing more physics. Okay, so here is tough. It's French, so but they give you the right amount of rigor, but also the right amount of real calculations. So other books are more focused on calculating, or I don't know. It's from the 80s, Michele. So anyways, putting back all the algebra, it turns out that this S matrix, if you want, on this S operator can be written as minus in states over the current exponential of plus in the current. When I multiply without indexes, I contract the indexes. Okay, mu mu. And the most relevant piece is this one. Okay. Where this capital letter is the Fourier transform of the current, and it's evaluated only on two of the well, on the real physical polarizations. So what is this S? S is a phase, sorry, a phase, not a phase, a number, and then these are operators plus. So remember that when you quantize, you divide your field into plus, sorry, A dagger and A operator. So those are the A dagger part of the field. Those are the A operators of the field. Okay. And that's it. So with this, now if you want to know what is the final state, you take, for instance, the vacuum, and you act on this, and this is going to be your final state. All right, and you see that it is not is quite complex, no, because it has all these plus operators that have to act on the vacuum many times. So it's not a single. It's not made of one single photon. It's made of infinite photons. Okay, and this is a coherent state. It's called a coherent state for reasons I don't want to enter into. But you see, it's very different from the ones that we were having before. The ones we had before, I already erased it, but this P is basically a plus operator of momentum P acting on the vacuum. Whereas this one has an exponential of A plus operators which multiply the current acting on the vacuum. Now, optical field has more to do with this kind of configuration than with single particles. Okay, and to describe it is going to be something like this. And if you want to know how many particles there are in this state, what you have to do is to compute, for instance, the number operator. The number operator of final, okay, it's going to give you an idea, and you can also do it in terms of momentum. Okay, remember, number operator is A plus A momentum. Okay, and you're going to see that the particles of this state is given by Poisson, a Poisson weight. So the particles is something we're going to see it later, so I'm not going to explain it much. But for each of the states, the distribution of how many particles there are of number. So what is the probability of having a state with m particles in this distribution is a distribution. And this is what, for instance, the light we are seeing here has. The light that is emitted classically is not photon, 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 photon. It's a collection of photons with a distribution, okay, given by this number. Okay. And when you emit gravitational waves, you have to imagine that you have the sources. The sources are classical sources. Then you have to do, it's more complex. You have to do a spin 2 quantization, not a spin 1, but in the end, it's going to be similar to this. Okay, so those are states that, again, are going to be important at some point in 20 minutes, apart from being very relevant for if you want to understand a classical source. So again, if anyone ever wonder, yeah, you can compute the average number of photons in a state of light emitted by a bulb, but it's not it's not a fixed number. It is distributed with these weights. All right. So in the universe, some signals may come to us as individual particles. Well, when I say individual particles, there can be a flux. Okay, there can be a lot of particles from dark matter hitting your detector, but individually, they are single particles in this sense. They can come to us as a coherent state. And then the next step is, okay, where if they are many particles and their distribution is not so easy, okay? It could be a completely crazy state, okay? So what do we do? And there is where ultralight dark matter is indeed living. How many in this room have heard the word light matter before me? Okay, not everyone. Well, so what is ultralight dark matter? Is dark matter which is quite light. You can ask my students that about my jokes. I don't know if they are happy or not. You're happy, Julia. Okay. Um, as I said before, the cause of the dark matter is not really understood. Well, understood, it's not quantified. And we already saw a limit, the GeV limit is a limit quite hard. Classical detectors. Being more clever, you can go up to MEV with the new concepts. Key electron ball starts to be really, really tough. Okay. Now there is even a different. There are other limits which are relevant and that we are going to discuss now. Key electron ball and paradigm. And then of course, yeah, there is some lambda way for dark matter, just to be comprehensive. There is also the possibility that dark matter is a bunch of matter going through the universe in particles. Description that is appropriate in a bit more. We are gonna forget about this, okay? Let other people care about this. Describe dark matter particles, okay, that may be generated in the early universe. And what questions that you may ask yourself, okay, now if I had to think about dark matter of particles overlapping and generating maybe a coherent state or a different state, or just as many particles that. So the question you can ask has to do with the picture of the galaxy as a fixed space. Your galaxy, let's say the Milky Way. Is there any Greek in the audience? A Greek speaking person? Milky Way. I don't know it, but yeah, Gala is milk, axis. You see, you learn many things. So you take the Milky Way, and the Milky Way, it has some size, okay? But it also has some size in momentum, right? You distribute particles. Well, let me just do it by bidimensionally, otherwise it's a mess. So in 2 dimensions, the size of the galaxy for visible matter is 10 kiloparsecs. For dark matter is 100 kiloparsecs for the galaxy of the Milky Way. And in momentum, the maximum momentum is the mass of the dark matter, escape velocity. All right? If particles velocity will escape because they are too to be kept. So that means that remember that phase space is quantized, right? The quantum of phase space is h bar. Okay. If I find a number of elements where I can put them in. How many? L cube by P cube divided by h bar cube. All right, this is the number of elements for me to start filling in my galaxy. If all of fermions, that's it. Bosons to have numbers which are bigger than 1. Okay, so this is important in order to understand, when are the different states in the galaxy having numbers. And then when this is going to be a more appropriate description. How do I know this? Well, I have to compare this with the number of states that I need. How many states do I need to fill the Milky Way? I take the mass of the Milky Way, and I have each state is not is mass. So the number of states I need it. Have to get the whole the Milky Way. All right. Each state has mass m, is the mass of the dark matter. And now by comparing, right? When this is true, h bar is equal to 1. When this is true, what happens that my states feel, in principle, when you feel states, you don't feel them equally. You know? For instance, in thermal equilibrium, there is a distribution. So here we are going to take the theory cow approach, spherical cow. And then, for instance, imagine that all of them have the same distribution. It's otherwise more complicated, and yeah, factor 100, not factor of 10 different, but that's fine. So this is size of the galaxy. This is m cube v cube. Then eventually, when the mass to the 4 is of the order of the energy density, right? Mass divided by volume, energy density, and then divided by velocity cube. Is the mass at which you start to fill with more than one particle per state. Okay. You can also see that this number corresponds. If you take the wave packet and you imagine that the size of the wave packet is given by the. Remember that from this relationship also the size of the wave packet is going to be given at least with the size of the average of the momentum, and you put here the minimum that you can have in this is where the momenta have the possible highest momenta, which is the escape velocity. You can see that this number also corresponds when to the moment where the size of the interdistance of particles is what smaller than the size of the particles. You find the same number. So when particles in the galaxy, in this case in 3 dimensions, start to overlap their wave packets, you find the same number. Okay, and that means that for lower mass, first find a classical result of dark matter called gun. Opa. The Engan bound tells you that the mass fermionic nature cannot be lower than 1 kilo electron volt. Of course, there are caveats to this. Below volt, like a white dwarf. It's really quantum Sure. Put more particles. You see, because you would like to put more particles, all the particle that you put in has to mass just fly away. And for bosonic, this is for fermions, okay? For fermionic dark matter. And for bosons, the same. For masses below that, large um, numbers of occupancy, and then the idea of describing them as individual particles starts to be not so intelligent. In this case, this depends on the to derive the bound. And one is where the density in dwarf spheroidals, okay, some kind of galaxies. But if we care about the Milky Way, we care about this number is order one. So for bosons, when you are around 1 eV in the Milky Way, has occupation numbers bigger than 1. Why we are now caring about the Milky Way? Because, in the end, we are trying to understand how to describe this in our surroundings. The galaxy, still the idea of individual particles makes sense, right? Depends on the. And in this case, this is what we call, there are different names. But typically, that's why I wrote the 1 eV. Sorry. 1 eV, okay? This is ultralight dark matter. Let's put it like this. At some point, people call it fuzzy dark matter. When you hear, typically, is when you hit the boundary, even though, as I said, this is random. And here is the Tremaine gun, which is very important for fermions. What else? And I'll give you as an exercise. That's these masses. What? But what happens in this super low regime? Exploding? No, it's not like this. It's something else. Okay, it's not so. I mean, the way is typically said is that at these masses, what is the momentum? No, the size of the wave packet is gonna be possible. Okay, because it's kilopascal, 100 pascal. You understand that these guys have the minimal possible size of the wave packets are kiloparsec size or parsec. So parsec is very big. Okay, so I'm telling you that you cannot put easily particles together at smaller distances. Then for sure it's gonna make an impact on galaxy formation in the early universe in Nyman alpha, in the late universe in the most smallest possible galaxies. Okay. All right. So let's now go and then study well what happens with this more this other way to describe dark matter, not as a collection of individual particles. Yes. Way to go and beat the Tremaine gun is what your colleague is saying. And for instance, imagining that there is even if you have two polarizations, you can have these numbers the number of degrees of freedom per field or something. To have 10 to the 20 species, 10 to the 30 species, and all this, yeah, is very different. Sure. Michele, you did 10 to the 32. Eh. Also, your supervisor. Yes. We have all things to hide. Or not, anyways. So now we are going to discuss in the last 20 minutes how do we describe this ultralight dark matter. So the bottom line that you read in papers is that let's take dark matter as a scalar field. Okay, it's a quantize, a field you have to quantize. Then there will be a state that characterizes the distribution of dark matter in the galaxy. And this is basically giving you the average, sorry, the expectation value of the field. And what people do all right, minus plus a phase. Okay, saying that for some oscillations, locally, you can describe it as a standing wave. Right? Those are non-relativistic fields. All right, so that's very different from light. Okay, so here, this is what basically is, and also with this being a non-relativistic distribution. So basically, all the waves that may be living in this configuration, because they are non-relativistic, their velocity is much more than 1, and eventually all of them oscillate with the same frequency m. All right, so this was what, again, this is a way to describe it. And a couple of years ago, some people thought, okay, look, can we do it a bit more carefully? And let me give you the reference. It's a beautiful reference. Okay, I can hit this. All right. 2408-04696. Okay, and the idea was, yeah, maybe that's nice, but also, what if we are about to be in the situation where this is valid? Can we understand this really at the level that we can explore all the phenomenology of these situations? And then what they did is basically, Rod et al., which is this paper, went back to what people have been doing in the 60s for the same question for optics. All right? So I have, in this case, a state of many particles, right? And I have a quantum field. For light can be a light emitted by a bulb. And then when is the description in terms of a classical field a good one, all right? And where, or in other words, where can I just use Maxwell's equations to describe light? In this case, when can I just use Klein-Gordon classical equation to describe dark matter? In this case, you see, this is the simplest dark matter model. You don't need to know quantum field theory. It's a classical field. And there are some subtleties, in particular having to do with the fact that here we are thinking about waves that are non-relativistic, and in light, in vacuum, light is always relativistic, right? So you cannot have the different waves of different frequencies oscillate differently. So the way to go is based on the on the formalism of assist many degrees of freedom, but you don't care about them, right? So this is called statistical mechanics. You only care about macroscopic objects. And for this, I have an observable, for instance, the energy density, right? And I have a double average. Why? Because the first average is because my distribution of particles is in a state, but also I don't know which state, right? So I have a distribution of states. So there are two averages. One because it's a quantum observable, and the second one because the system is not in a characteristic state. It's basically on an average state. So to describe this, one just can know the probability distribution in a particular basis. Right here I say there is a characteristic, basis of states, and if I know what this is for each of them, I can compute all the things I want. Another way to write this is I introduce here the identity. By the way, also I'm not going to be careful with the continuous versus discrete states. I'm most of the time going to write sums, and if there are some subtleties, I put them under the rug, and they are in the books. Okay. So here, if I have um, I resolve the identity with a certain collection of states. I plug it here. Okay, and this is identical to n phi o n. Now there are two traces, one from this one, sorry, two sums, one from this one. And you see, what do I have here? I have a sum of the weights of each of these operators. Okay, this is an operator acting on the Hilbert space, and now sum, as a trace. So this is equal to the trace of rho O, where rho is equal to sum of phi p phi. This is called the density matrix of the system. So basically it's telling you for each projection, those are projecting operators. They project on the basis that you want. So I project on this basis, and each of these projections has some probability of being, the ones that you find in the system. So if you want to find any average, any expectation value, the only thing you need to do is to trace the operator you want to find with this other operator, which is called matrix. Right, and now the theory of quantum statistical mechanics for particular configurations. All right. Now, what is this guy for dark matter in a galaxy? In principle, this question is very complex. It's a very complex question. It requires understanding what's going on with the different particles, generating hard to compute configurations, except if you are Glauber and Sudarshan, and you decide to, instead of using the number of states basis, you describe things in terms of coherent states. So this is an amazing, to me, piece of physics, and it has to do with the fact that when you, again, you want to compute any operator. So let me start from a quantum theory of fields, okay, where I have Yeah, I don't know why I'm doing it so carefully, but that's what it is. Okay, so you have a field which is quantized. Right? In this case, well, and this can transform into a sum when you do it in infinite volume. And now you want to compute the operator related to this field. For instance, any observable, all right, coming from the field. It can be the field itself. Sorry, the observable can be the field itself, or it can be the field square, whatever, right? So let's write operators like observables generically as O's. You take now this formula. By the way, I most likely will forget about the two. We'll write only one, okay? In the end, is the average, right? The expectation value, and you take everything into account there. And you can do what we write before. So you can have this formula here. So you take rho O n n sum over n. If you write it as even, what is this? So it turns out you can also write it as, you can take the matrix itself, so the density matrix, and write it not as P phi, not in this basis, but you can also write it in a different basis. You can write it, for instance, in the number state basis. Okay, so you might know that I want to compute, and well, in order to compute it, I want to have my matrix in the most adequate basis. And as up to now, we are used to having this as a good basis, the focus states, right? And then if I take the operator, I compute the expectation value of the number state, and I weight it by a weight that tells me what is this density, sorry, what is the typical weight of these guys. So first, this is nothing easily computable unless you evolve particles and eventually tells you how they are distributed in number states. But I told you that classical states don't like this basis. So you eventually have something that looks like classic. This is going to be something very, very hard to find just by easy algebra. Also, one must be careful when one derives these equations, because these are not probabilities always. Okay, so then they can be negative, right? In this case, when the basis is complete, things are fine, but one must be careful when they change basis. Anyway, but the most important thing is, how do you compute these probabilities? So what the Sudarshan and Glauber realized is that there is one basis for which you don't need to do anything. All right? There is a kind of a central theorem. Remember the central theorem that tells you that whenever you have a system with many degrees of freedom, the final distribution is Gaussian. And the only thing you need to know is the width of the Gaussian. That's it. So when you use coherent states, okay, defined as for each momentum Remember that they were generated by exponentiation of the A dagger and A operators. Okay. So the coherent state characterized by alpha k is you take the vacuum and you then generate a complex, well, not complex, it's very simple. It's an exponential, but a state that has many particles around. The number is not a state with fixed number of particles, okay? The amazing thing is that this is a basis, over complete basis of the Hilbert space, okay? So in principle, you can also this kind of traces or this kind of sums with these states, okay? A way to see that it is a basis is that you can project it to, for instance, you can project it in terms of number states, invert it, and find something like this. Alpha k to the n. All right, so number in the in the momentum k, the number state can be, well, you can write the coherent state as a collection of states with, as I said, with all possible particles in them. Okay, so in principle, coherent states, in this sense, are the really complex in Fock states. And the relevant thing is that the density matrix can be written as k. Alpha is complex, as you can see. Okay, it's a complex number. So you integrate over alpha k, all of them. There is a probability distribution of alpha. Okay. Here is the projector in the state. All right. And now is where the miracle happens, is that one can show that when the distribution is made of many particles, let me state you exactly what it is, the theorem, because for a configuration with any independent and identically distributed random fields, okay, of these alphas, eventually this is P of alpha is given by pk 1 over pi nk e. All right, so the distribution of particles that don't interact with each other and they are independently, and there are many of them interacting together randomly, generates a kind of Gaussian form for the P alpha, where the only information that you need to know is this number, and this number is the average, sorry, the expectation value of the number density operator. Right? First, I leave it here, but this is the first amazing thing about coherent states, is that for this kind of distributions that are in principle very hard to handle because of the Gaussian theorem, the only thing that you need to know is the number of particles per. That's completely your distribution. Of course, there are some assumptions behind. The typical assumptions are are the ones that characterize galaxies, okay? That the particles have been flying around for many, many years, and I need to know typical number per momentum, and this is in realized situations by some thermal light distribution of virial light distribution. When you do dark matter, is extracted from some kind of distribution. First, you can get from simulations, but also analytically, it makes sense. It's a kind of virial distribution of momentum. And tomorrow, we will start with this and with the second characteristic of, so far, we didn't see anything looking like a classical field, okay? The only thing I told you is that with these states, the density matrix is only characterized by the number of particles per unit, sorry, per momentum n of k. But the second thing that is going to be quite amazing is that you take any operator, you normal order it, okay, and then the you know, when you compute this average, this is going to be equivalent to taking the average with the probability distribution before and where the operator is taken as a classical field. Okay, so here, in principle, this operator depends on A, K, and AK dagger. Okay, when you do things in terms of coherent states, any kind of observable can be computed as a distribution function acting on a classical equivalent of the quantum operator. What is this? Alpha k is exactly, for instance, that means that if I had before phi written like this, now I have to substitute A by alpha, you see? It's basically telling me that the values of the amplitude, okay, whatever multiplies the E or the two exponentials is distributed according to the distribution of alpha. So it's really like having a classical field with amplitude distributed according to this. Okay, and that's the way in which classical stochastic variables arise from all this quantum formulation. Okay. Yeah. Where to look for this? Well, look at the paper. I think it's very well explained. I think we can stop here, and tomorrow we will continue. Thank you.